You are suspended now in a quiet, deep twilight, where the air holds the coolness of ancient moss and wet river stones. Feel the steady, gentle current passing beneath you, a whisper of water over smooth, dark earth. There is only the rhythmic, slow pulse of time itself, a distant, comforting beat that settles deep within your chest. Let the sense of petrichor and damp loam drift up to meet you, creating a perfect stillness, allowing every ripple of tension to finally settle and dissolve into the quiet dark. Chapter 1, Entering the Pattern Stream. Slowly, gently, we begin this profound journey, a passage into the heart of mathematical beauty, a landscape defined not by sharp edges, but by elegant repetition. We are tracing the architecture of existence itself, exploring the concept of self-similarity, a whisper that whispers across the vastness of physical reality. To understand this hidden harmony, we must simply quiet our minds and allow our attention to drift toward patterns. Think of patterns not as rules, but as echoes. An initial gesture, a simple curve that repeats itself, slightly altered, across scales ranging from the visible to the profoundly minute. This is the fractal nature of the world, a deeply sophisticated language spoken through simple, recursive geometry. Imagine looking closely at a fern frond and noticing that the swirl of the tiny leaflets, the pinny, mirrors, almost identically, the larger curve of the main stem, which in turn echoes the sweeping arc of the entire leaf structure. This correspondence, this remarkable visual recursion, suggests an underlying, unwavering mathematical order, woven into the warp and weft of natural processes. We start our contemplation with the feeling of watching water. Picture a shallow, undisturbed river during a season of steady flow. Where the river meets its delta, the water does not simply spread out. It replicates its branching pattern. Each tiny, subsidiary stream that peels away from the main current maintains the same general geometry as the main flow itself, just scaled down. The principle governing this complex network might be simple: the necessity to maximize the surface area in contact with the ground, but the resulting visual structure is breathtakingly intricate. Look at the patterns etched into the sediment, the miniature tributaries, each one mirroring the grandeur of the primary river artery. This is the soothing revelation of fractal geometry. That complex grandiosity can emerge from the simplest of mathematical instructions, yielding no messy complexity, but perfect, repeatable order. Consider the lightning strike, a transitory sculpture rendered in light. When a colossal bolt tears across a cloud-strewn sky, its path is seldom a straight, clean line. Rather, it develops smaller, subsidiary forks branching off the main conducting thread. Each smaller fork retains the branching character of the larger structure, echoing its main path in a miniature, dazzling reduction. The mathematics governing this aerial phenomenon suggests an optimal path of heat dissipation and electrical potential flow, resulting in a structure that is simultaneously chaotic and profoundly ordered. We observe a kind of natural optimization, where complexity is the most elegant solution to a physical problem. This natural propensity for repetition transcends mere visual resemblance. It is an intrinsic signature of self-organization. When natural systems encounter a constraint, be it the need to draw nutrients from a limited volume of soil, or the need to spread energy quickly through an air mass, they tend toward fractal-like efficiency. The mathematical models are not merely descriptive, they appear to be predictive of the ultimate, stable shape of growth itself. We are witnessing the universe fulfilling an inherent need for efficiency, expressing depth within a limited space, and doing so with a pervasive, comforting rhythm of repetition. Chapter 2, the galactic web and branching life. Our gentle exploration now takes us outward, far beyond the green canopy of terrestrial life, across the deep velvet expanse of the cosmos. Here, the principle of self-similarity manifests in the colossal, sweeping arms of spiral galaxies. When astronomers map out the luminous trails and dust clouds that constitute these celestial bodies, they often find that the distribution of matter follows patterns that resonate with earthly fractal geometry. The large, sweeping spiral arms are formed by gravitational forces that operate over unimaginable distances and immense stretches of time. Yet, if one zooms into the patterns of star clusters within those arms, or observes the accretion disk of a distant young star, the same geometrical echo appears, merely scaled up or scaled down by factors of millions of light years. The structure speaks of universality. Whether we are counting the intricate branches of a delicate redwood root system, anchoring itself into nutrient-rich earth, or observing the filaments of gas forming a great cosmic web between galaxy clusters, the underlying geometric logic remains remarkably consistent. This constancy suggests a foundational mathematical rhythm that underpins organic growth on Earth and the formation of stellar architecture beyond our solar system. It is a soothing realization that the rules governing a leaf developing on a rainforest plant are fundamentally connected, conceptually and mathematically, to the rules governing the distribution of matter in the distant reaches of the Milky Way galaxy. We can apply this conceptual lens to biological structures with a precision that is almost mesmerizing. Consider the human lungs, a marvel of internal engineering designed for maximum gas exchange. The branching pattern of the bronchi and bronchioles is not arbitrary. It is a fractal tree structure, designed to maximize the surface area available for oxygen absorption while minimizing the metabolic cost of building and maintaining complex pathways. Each major airway branches into smaller, progressively finer tubes, repeating the pattern of division until it reaches the minute level. The total resulting surface area far exceeds the size or shape of the organism itself, a perfect geometry of resource utilization. Another stunning example is found in the structure of trees themselves. The way a tree distributes its canopy, the arrangement of major limbs into smaller branches, and those smaller branches into petioles supporting individual leaves, is a textbook example of optimal resource distribution, a biological manifestation of fractal rules. The branches strive to minimize the distance between the light-capturing surfaces, maximizing the exposure to the vital energy source. When we trace these branching networks, whether they are formed by ancient river systems meandering through a plateau, or by the microscopic veins carrying life-giving sap through a deep forest trunk, we see the same profound mathematical imperative at play. The rivers, in particular, form what specialized geologists call dendritic drainage patterns. These patterns, visible when gazing at old maps or tracing the flow paths across a satellite image, demonstrate incredible self-similarity. A small stream flowing over a gently sloping plain often mimics the path of the larger river system it ultimately feeds into. Erosion, the slow, persistent action of water over geological epochs, follows this mathematically predictable fractal geometry. The material world, therefore, is patterned not by chance, but by a sustained, patient adherence to geometric efficiency. Chapter 3, Mathematics of Repetition, the Mandelbrot set and natural analogues. Our gentle journey guides us now into the abstract beauty of mathematics itself, where the concept of self-similarity was formalized most poetically in the notorious Mandelbrot set. This particular fractal, visualized through a complex equation, demonstrates infinite detail within finite boundaries. It is a mesmerizing image, a dark, swirling map where zooming in never reveals empty space, but only more complexity, more interwoven beauty. The core mathematical statement is incredibly simple, yet its visual consequence is boundless and infinitely intricate, providing a deep, humbling lesson in geometric potential. While the Mandelbrot set is a construct of pure mathematics, its existence provides a powerful model for understanding natural analogues. Nature, in its relentless quest for equilibrium and efficiency, seems constantly to be solving equations similar to the underlying principles that generate these mathematical wonders. The appearance of fractal patterns throughout growth, branching, and decay suggests that the mechanisms of self-organization on Earth and in the cosmos are profoundly intertwined with these underlying mathematical principles. Consider the vascular system in an animal, a complex network of arteries, arterioles, and capillaries. Just like the river delta, the circulatory system exhibits remarkable fractal characteristics. To ensure that every single cell receives adequate, even flow of oxygenated blood, the vessels must branch repeatedly, each smaller vessel pattern mirroring the function and structure of the larger feeder pipe. This intricate scaffolding, running through the delicate tissues, is a functional art form, a testament to the mathematical elegance required for life to sustain itself. We can further contemplate structures like the Roman venation of a large leaf. These microscopic rivers across the leaf's surface are engineered systems, delivering sap and nutrients. Look at the main veins dividing into smaller networks, which then divide again, segment by segment. This hierarchical structure ensures that even the tiniest cell receives sustenance, mapping the large, overarching structure down to the microscopic level while maintaining functional integrity. It is a pattern of perfect, proportionate division. The concept of dimensionality also comes into play here, suggesting that highly complex natural objects often occupy a geometric space that possesses fractal dimensions, rather than simple integers. This subtle dimension relates to how effectively the object fills the space it occupies. The fractal efficiency allows these natural systems, whether they are lungs, coastlines, or river deltas, to achieve an extremely high degree of functional complexity using materials and energy with minimalist efficiency. It is a sublime orchestration of geometry. Chapter 4, the Coastline Paradox and Scale Invariance. Our focus drifts gently toward the scale dependency of pattern recognition, encapsulated beautifully by the theoretical coastline paradox. One might measure the perimeter of a continent, starting with a blunt ruler, obtaining one measurement. Then, using a smaller ruler, the measurement appears longer, capturing smaller bays and inlets. If we continue to use progressively smaller rulers, down to the size of a single grain of sand, the purported perimeter would theoretically approach infinity. This paradox is not a flaw in mathematics, but rather a profound illustration of how measurement is tied to the scale at which the observation is made. It teaches us that when dealing with natural boundaries, especially those formed by erosive forces like water or wind, the concept of a single, fixed measurement breaks down. The boundary is inherently fractal. It contains structure at every scale of observation. It suggests that the total complexity of a natural frontier is dependent entirely on the level of detail we choose to perceive. This principle of scale invariance is everywhere, appearing perhaps most beautifully in the study of rock formations. Picture the sedimentary rock face, sculpted over millions of years by water and wind. The cracks and fissures, when viewed from a modest distance, suggest a certain pattern. But if we look closer, we see that these cracks initiate smaller cracks, which in turn initiate even tinier fractures, repeating the signature of the initial larger break at progressively smaller scales. The resulting cliff face is a vast, three-dimensional fractal tapestry. This concept extends deeply into the understanding of atmospheric physics. The distribution of cloud formations, the paths of wind currents, and the massive, sweeping structures of dust plumes often display fractal characteristics. Weather systems demonstrate a continuous interaction across multiple scales, from the large, continental high-pressure zones down to the localized, micro-scale eddies detected by high-altitude sensors. The physical laws governing energy transfer and fluid dynamics mandate this geometric self-replication. To observe nature through this lens is to realize that there are no truly small details or large holes. Everything is linked by shared geometric principles. The mechanics of continental uplift, the resulting fault lines and rock fractures, echo the rules governing the formation of tiny spiderwebs. The entire physical landscape is participating in a grand, deep-time fractal conversation, whispering secrets of mathematical economy across epochs of change. It is a comforting realization of underlying systematic harmony. Asterisk Chapter 5, Bioluminescence, Sprouting, and Optimized Growth. Let us now shift our focus to the mechanisms of life, how life itself designs structures to be optimally efficient. Many biological growth processes, whether it is the vascular network of a plant or the propagation pattern of a coral reef, are governed by fractal algorithms designed to maximize resource capture and minimize energy expenditure. This pursuit of optimal growth yields shapes that are mathematically exquisite. Consider the branching of mycelial networks, the underground filaments of fungi. These networks spread outwards, seeking sources of sustenance deep within the soil matrix. Their growth pattern is characteristically fractal, diffusing into the surrounding earth in a highly efficient, spreading lattice. They do not waste energy moving through redundant pathways. Instead, they expand outward, replicating the branching pattern of the last absorbed nutrient source, spreading knowledge and sustainment throughout the subterranean environment. Another compelling biological analogy is found in the way crystals form. Crystal structures, from quartz veins in ancient mines to the minute internal crystalline structure of certain gemstones, frequently display fractal-like patterns of growth. The growth doesn't happen uniformly. It builds outward in repeating facets and angles, governed by the inherent crystalline chemistry seeking the lowest energy state of arrangement. This slow, geological self-ordering process embodies structural perfection. Even specialized systems, such as the branching of root hairs on plant roots, exhibit this refined fractal efficiency. These microscopic hairs expand into the soil, maximizing the surface area for the absorption of essential elements like phosphorus and nitrogen. The root structure, therefore, acts as a highly optimized, complex biological plumbing system, where every tiny division serves the massive, overarching goal of total system survival and energy intake. When we examine the growth of corals, we also see a clear adherence to such rules. The polyps deposit calcium carbonate skeletons, and their expansion seeks to maximize the surface area available for absorbing light and nutrients from the surrounding, highly complex marine environment. The resulting reef structure is less a collection of simple branches, and more an emergent, three-dimensional fractal mass that continues to grow, echoing its own past structures in continuous, slow-motion repetition. This is life's mastery of sustainable, self-similar architectural principles. Asterisk Chapter 6, The Deep Ocean and Sediment Dynamics Asterisk. Our gaze now travels downward, into the deep, quiet embrace of the ocean floor, where life and geology interact through forces of immense pressure and slow, relentless change. The ocean environment provides a vast, constant laboratory for studying fractal dynamics, particularly in the movement and deposition of sediment. When a submarine landslide occurs, the resulting flow of mud and sediment does not flow in a straight or predictable line. The resulting structure, known as turbidity currents, develop complex fractal patterns of deposition. These patterns, the lobe deposits, show a recursive self-similarity. Close-up sections mimic the patterns seen much farther out in the flow. This is a direct manifestation of fractal geometry in physical processes. Pause. The interplay of deep-sea currents and plate tectonics also generates fractal geometries. The coastline of any continent, studied over vast stretches of time, exhibits a statistically self-similar roughness, regardless of whether you study it from satellite altitude or from a coastal boat. The fractal dimension of the coast reflects not geological caprice, but the underlying mathematical constraints governing the fluid dynamics and erosion rates. Pause. This connection suggests a universal language of pattern, that the physical laws governing a slow geological creep are mathematically analogous to the laws governing a rapid fluid flow or the biological scaling of a leaf structure. The universe seems to express complexity through underlying simplicity. Pause. These deep-sea phenomena serve as silent reminders that the familiar, jagged beauty of the Earth's shape is deeply encoded with patterns of profound mathematical regularity, patterns that repeat across vast scales and immense timescales. Pause. The realization of this underlying mathematical harmony is a profound way to contemplate the physical world, to see the pattern not just as visual, but as mathematically predictable. Pause. The final message whispered by these natural formations is one of continuity, that the forces that shaped the mountains millennia ago are the same forces structuring the micro-detail of the sediment today. Pause. It invites us to look closer, to appreciate the infinite repeating beauty found in the measurable language of geometry. Pause. It is a profound invitation into the beautiful pattern of existence itself. You are suspended now in a quiet, deep twilight, where the air holds the coolness of ancient moss and wet river stones. Feel the steady, gentle current passing beneath you, a whisper of water over smooth, dark earth. There is only the rhythmic, slow pulse of time itself, a distant, comforting beat that settles deep within your chest. Let the sense of petrichor and damp loam drift up to meet you, creating a perfect stillness, allowing every ripple of tension to finally settle and dissolve into the quiet dark. Asterisk Chapter 1, Entering the Pattern Stream. Slowly, gently, we begin this profound journey, a passage into the heart of mathematical beauty, a landscape defined not by sharp edges, but by elegant repetition. We are tracing the architecture of existence itself, exploring the concept of self-similarity, a whisper that whispers across the vastness of physical reality. To understand this hidden harmony, we must simply quiet our minds and allow our attention to drift toward patterns. Think of patterns not as rules, but as echoes. An initial gesture, a simple curve that repeats itself, slightly altered, across scales ranging from the visible to the profoundly minute. This is the fractal nature of the world, a deeply sophisticated language spoken through simple, recursive geometry. Imagine looking closely at a fern frond and noticing that the swirl of the tiny leaflets, the pinny, mirrors the overall arch of the larger frond. This internal echoing suggests a universal blueprint, a fractal geometry inherent to organized matter, a whispering echo of pattern across scales. We see this principle manifested in the structure of a snowflake, where the six-sided symmetry repeats itself at minuscule levels, a perfect, crystalline recursion. Or in the branching of lightning across the night sky, forming dendritic patterns that branch, and branch away from a single, intense point of energy. Whether it is biological structure, whether phenomena or geological formations, the mathematical pattern suggests an underlying efficiency, a blueprint optimized by natural selection for minimal energy expenditure and maximal surface area interaction. The geometry of efficiency. The concept of the optimal structure that maximizes interaction between two different mediums, say, oxygen in the blood or light in a mirror, is often dictated by fractal rules. The lungs, with their intricate alveolar structures, provide an enormous surface area within a relatively small volume. This is the embodiment of geometric efficiency. The river deltas, branching out across wetlands, similarly maximize freshwater dispersal across the landscape. Nature, it seems, favors the mathematical elegance of the fractal, the infinitely repeating pattern that speaks to both complexity and economy. This efficiency is not arbitrary. It is the persistent physical law of least effort for maximum result. To understand the geometry of the universe is, in many ways, to study the elegant, repeating rules of iteration. The patterns we observe are less about random occurrence and more about fundamental principles of energy transfer and material organization. The mathematics of self-similarity. Self-similarity is the core concept here. If you zoom in on a part of the pattern, you find a scaled-down replica of the whole pattern, and if you zoom out, you find the pattern repeating again. This concept, formalized by mathematicians like Benoit Mandelbrot, provides a framework for describing natural forms that defy simpler Euclidean geometry. Consider a coastline. If you measure it with a large ruler, you get one length. If you use a smaller ruler, you measure intricate bays and peninsulas, yielding a longer measurement. If you use a millimeter, you are measuring individual barnacles and rocks, making the measured length even greater. The coastline paradox confirms that the perceived length depends entirely on the scale of measurement, highlighting the inherent, scale-dependent complexity of natural systems. This inherent variability is what the fractal dimension quantifies, the fractional number between an integer dimension, like a line, dimension 1, and the dimension of embedding space. It measures how complexly a shape fills the space it occupies. The study of these dimensions moves us from simple description to predictive modeling. It suggests that the universe can be modeled by a limited set of recursive rules applied across a vast range of scales, from the quantum foam to the largest galaxy clusters. Section II, the Earth's patterning. From tectonic plates to river networks. When we zoom out from the molecular scale to the planetary one, the fractal patterns persist, guiding the structure of the Earth itself. The distribution of tectonic plates, the faults along the San Andreas Canyon, or the massive cracks in dry lake beds all exhibit fractal geometries. These fractures are not random. They follow stress lines that distribute energy most efficiently across the planetary crust. Likewise, river networks, the tributaries branching out from major sources, are classic examples of fractal drainage systems. They strive to drain the entire drainage basin using the least amount of energy, resulting in highly efficient, repeating arterial patterns. These patterns reflect the interplay between gravitational forces, rock resistance, the Mohs scale of hardness, and the necessity of creating a steady, low-gradient flow line. The geological past is inscribed by these fluid, repeating patterns. Ancient erosion carved deep gorges. The pattern of faulting reveals past moments of intense crustal stress. These patterns are geological time capsules, allowing us to map the mechanical movements of massive systems over millions of years. Climate, pattern, and feedback loops asterisk. Even the abstract systems of global climate are governed by complex, repeating patterns. Ocean currents, like the massive conveyor belt circulation, move heat and nutrients across hemispheres in predictable, massive cycles. The El Niño Southern Oscillation, ENSO, being the most famous example of a repeating, interconnected global pattern. These systems demonstrate positive and negative feedback loops, where a change in one variable triggers a cascade of proportional responses across the entire interconnected system. For instance, warmer ocean water reduces the density of the surface layers, altering the rate of deep-sea mixing, which in turn affects global carbon sequestration. Understanding these interconnected, recursive feedback loops is crucial, offering a model for how global systems maintain and how they can destabilize under external pressure. Section III, the living tapestry. Biological recursion and optimal design. The biological world is perhaps the most perfect realization of fractal geometry. The development of trees, with their branch structures that mirror the overall shape of the trunk, adheres to fractal rules. The human respiratory system, as discussed, is a prime example of maximizing surface area via recursion. The venation of leaves, the patterns of veins, is mathematically similar to river networks, an optimized plumbing system designed to transport resources efficiently across a flat surface. Even the distribution of neurons in the brain, which forms vast, interconnected networks, exhibits fractal properties that are hypothesized to be linked to optimal information processing efficiency. In medicine and biology, recognizing these fractal patterns allows researchers to optimize drug delivery systems, tailoring them to mimic natural fractal growth patterns to ensure maximum absorption across complex tissues. It moves pharmacology from brute force dosing to pattern-based precision. Self-organization and emergence. The most profound implication of observing these repeating patterns is the concept of asterisk self-organization asterisk asterisk. Self-organization refers to the ability of a complex system to develop order and structure without external guiding intelligence or blueprint. Life itself is the ultimate emergent self-organizing system. A flock of starlings forming a murmuration or a school of fish moving as a unified body do not need a central leader. Each individual adheres to simple, local rules, maintain safe distance from neighbors, match the speed of neighbors, move toward the perceived center. The collective, emergent behavior, the stunning, fluid geometric pattern, is far more complex and beautiful than the sum of its individual parts. This reveals a deep principle of nature. Complexity often arises not from the genius of a singular planner, but from the simple adherence to elegant, local rules that interact recursively across a self-contained system. Conclusion, the language of pattern. The recurring theme across geology, biology, meteorology, and physics is the undeniable presence of the asterisk asterisk fractal pattern asterisk. It suggests that the universe, in its staggering diversity, speaks a common, ancient language, the language of efficient recursion. To master this language is to understand the fundamental constraints and potentials of matter. It moves our focus from asking asterisk, who designed these systems, to understanding how they must be organized to function at the lowest possible energy cost while maximizing their interaction with their environment. The universal geometry points toward a universe built not on accidents, but on profoundly elegant, mathematically optimized repetitions, a ceaseless, beautiful echo across every imaginable scale.